Hi, this is lecture number 2 on infinite series. In lecture number 1, we have discussed about infinite series, behavior of infinite series, convergent and divergent of infinite series, and Cauchy's convergence criteria for series, and some examples and a few results related to infinite series. So quickly revise Cauchy criteria for convergence for series. So given any epsilon greater than 0, any epsilon greater than 0, however small, we fixed, there exists a positive integer p, that is p belongs to set of natural number, such that mod of Sn minus Sm for all n greater than m greater than equal to p, Sn minus Sm is less than, such that Sn minus Sm is less than epsilon. Or we can write this such that mod Sn minus Sm is less than epsilon. Sn is the sum of first n term of the series. Sm is the first m term of the series. Right? So, or we can, here Sn is a1 plus a2 plus an, where the given series is summation an. If we have a series, summation an is given, right? And Sm is a1 plus a2 plus am. So because n is greater than m, so n is greater than m, so Sn minus Sm is equal to a1 plus a2 plus an, even because n is greater than m, so m comes in between 1 and n, so am plus 1 plus an, this is Sn, minus Sm is a1 plus a2 plus a3 plus an. So if we take the modulus, then this. So we can write this as mod of a1, a2 up to am, all the terms are cancelled out. So we have only am plus 1, am plus 2, plus so on. Okay. And our goal is to show that this is less than epsilon. If this is less than epsilon for all n greater than m, greater than equal to p, then we can say the given series is Cauchy sequence. The given sequence is a Cauchy sequence and it converges. Right? We have also discussed one important result, important theorem, that is, if summation n equal to 1 to infinity converges, then limit n goes to infinity, an equal to 0. So we can, we have already proved this in our first lecture, and we know that if we have a statement like if P then Q, if we have a statement if P then Q, then what is the contrapositive of this statement? The contrapositive of this statement is if not Q, then not P. So this is the contrapositive of this statement. So if this is true, if statement is true, then its contrapositive is also true. If statement is false, its contrapositive is also false. It means we can say both the statements are equivalent. If we have S1 statement, S2 is the contrapositive of S1, then we can say S1 and S2 are equivalent. S2 are equivalent. So now, because we have a statement, if summation an converges, then limit n goes to infinity, an equal to 0. So what is the contrapositive of this statement? This is P. If P, then Q. This is Q. Right? So what is the contrapositive of this statement? If not Q, then not P. So we can say corollary of this statement. If limit n goes to infinity, an is not equal to 0. Not Q means limit an is not equal to 0. Then not P. Then summation of an is not convergent. So both are equal. Next important result is if we have a positive term series, an is greater than 0 for all n in n, right? And we have partial sum Sn that is equal to a1 plus a2 plus so on an. Then the series summation n equal to 1 to infinity an converges if and only if sequence Sn is bounded above. So this is the first part of the theorem, that is we have a positive term series and we have a partial sum Sn of the series a1 plus a2 plus an. The series converges if and only if it is bounded. We can also write this as that is, or we can write summation an is convergent if and only if sequence Sn is bounded above. When we say a sequence is bounded above, if it has upper bound, right? So if and only if there exists a positive real number k greater than 0 such that Sn is less than k for all n in n. Or we can say such that for all n in n, Sn is less than k. If this happens, then we can say the series summation an is convergent if and only if it is bounded above. Or if we have a positive term series, it is bounded above, then it is convergent. Right? What is the second part? The series the second part is the series summation an diverges to infinity. Summation n equal to 1 to infinity. An diverges to infinity. Why we say it diverges to infinity? Because we have a positive term series. Right? If it diverges, then it diverges to plus infinity. So if the series summation an diverges to infinity, if and only if the sequence is, what is the condition? The sequence Sn is unbounded above. Unbounded above. So how can we write this? if we write the complete condition, that is, we have an is greater than 0 for all n in n, and we have sequence Sn is a1 plus a2 plus an. The series an diverges. When it diverges, if and only if summation an diverges to plus infinity. That is important because we have a positive term series. So if it diverges to plus infinity. If and only if for any, you can take any k. For any k greater than 0, however large you can take. There exists a positive integer m, that is n belongs to n, such that Sn is greater than k for all n greater than equal to n. Or we can say, we can write such that for all n greater than equal to m, Sn is greater than k. Okay. After this number, if we have k, this is the large number, or we can take k to be somewhere here. So after some number, if we have mth number here, so Sm is less than k. But even if we take m minus 1 here, Sm minus 1, what happen if we take Sm, m, or all number m plus 1, so Sm is greater than k. So the sequence is unboundable. It means this series is not convergent. It diverges, and it diverges to plus infinity. So now we will do some examples related to Cauchy sequence. So example number 1. Apply Cauchy's criterion to prove that the series summation 1 upon n square is convergent. So we have the given series. Here the given series is summation an is equal to summation 1 upon n square. So here an is equal to 1 upon n square, which is greater than 0 for all n in n. You can take any n, so an is greater than 0. So we have a positive term series. Right? So let given any epsilon greater than 0, given any epsilon greater than 0, however small, and for n greater than n, and we take n greater than. Okay. So we have to show that mod of Sn minus Sm. So Sn minus, we can take there exists P belongs to n such that for n greater than m greater than equal to p, for all n greater than equal to m greater than equal to p, mod Sn minus Sm is less than epsilon. This we have to prove. We have to show that. Right? So we start from left hand side, Sn minus Sm. What is Sn minus Sm? Sn means A1 plus A2 plus An minus Sm means A1 plus A2 plus An. Since m is greater than n is greater than m, so we have more number of terms in this part as compared to second part. So when we subtract the first m terms of this, these are cancelled out. So we have only am plus 1 plus am plus 2 plus am plus 3 plus and the last term am. Because all the terms are positive, so we can write this as am plus 1, am plus 2, because an is greater than 0 for all n belongs to natural number. It is given. So we can write this as am plus 1 plus am plus 2 and so on. And what is am plus 1? An is 1 upon n square. So am plus 1 is 1 upon m plus 1 whole square. Am plus 2 is 1 upon m plus 2 whole square. Am plus 3 1 upon m plus 3 whole square plus an is 1 upon m square. So in morning, in today's lecture, that is lecture number 1, we have discussed that if we have to find a relation A is less than or equal to B. So sometimes what we do, we go A is less than or equal to some lambda, lambda is less than or equal to some mu, mu is less than or equal to some delta, delta is less than or equal to B. So for going A to B, we have to find a relation that is A less than lambda, lambda less than some number, that number less than some number, and to reach B, we have to follow a chain. Right? So what we do, we use the same concept. We use the same for this part also. Because we can write this one as, now I do some calculation part here. That is, we know that m plus 1 is bigger than m, right? So if we multiply both sides by m plus 1, then m plus 1 ka square is greater than m into m plus 1. For all m belongs to natural number. It is true for every natural number, right? So 1 upon m plus 1 ka whole square is less than 1 upon m into m plus 1. Right? Is it clear? So similarly, m plus 2 is also greater than m. M plus 2, if we multiply both sides by m plus 2 is greater than m into m plus 2. So we can write 1 upon m plus 2 ka whole square is less than 1 upon, even this is m plus 1. So we can write this as m plus 1 into m plus 2. So we can write m plus 1 into m plus 2. Right? Similarly, up to 1 upon n square, we can write this as 1 upon n minus 1 into n. So we follow the same result, and we can write this as this is less than 1 upon m into m plus 1 plus 1 upon m plus 1 into m plus 2 plus 1 upon m plus 2 into m plus 3 plus 1 upon n minus 1 into n. And since this is equal to, this is same as 1 upon m minus 1 upon m plus 1. We can separate this. We can write 1 upon m plus 1 into m plus 2 as 1 upon m plus 1 minus 1 upon m plus 2 plus 1 upon m plus 2 minus 1 upon m plus 3 plus so on 1 upon n minus 1 minus 1 upon n. But we observe all the terms in the brackets are cancelled out except we have only 1 upon m minus 1 upon n. So, and this is less than equal to 1 upon m. Less than equal to 1 upon m because 1 upon m minus some positive number, it is less than or equal to this. So now we have Sn minus Sm is less than 1 upon m, but our goal is to show that this is less than epsilon. This is less than epsilon. So this is only possible if 1 upon m is less than epsilon. So this implies mod of Sn minus Sm is less than epsilon if 1 upon m is less than epsilon. Now from here, we have to find a number m. After which number, the difference between Sn and Sm should be less than epsilon. So which property gives us this number, right? So Sn minus Sm is less than epsilon if m is greater than 1 upon epsilon. Now, since we know that nx is greater than y by Archimedean property, what is Archimedean property? If x comma y belongs to R such that x is greater than 0, there exists a natural number n in n such that n into x is greater than 1. If we take y equal to 1 and x equal to epsilon, so what is this? N into epsilon is greater than 1. This implies that n is greater than 1 upon epsilon. So by which property we get? This is by Archimedean property. So by Archimedean property, now by Archimedean property, we can choose, or we can say there exists a positive integer property. There exists m belongs to, or we can say p belongs to natural number such that p is greater than 1 upon epsilon. P is greater than 1 upon epsilon. Then mod of Sn minus Sm is less than epsilon for n greater than m greater than equal to p. So this implies that sequence Sn is a Cauchy sequence. Sn is a Cauchy sequence and the given series is converging. And the given series summation n is convergent. So even we can directly write this as, because the given series summation n is convergent. So similarly, we can do summation n equal to 1 to infinity 1 upon n की power p for p less than equal to 1. is divergent. Show that this is divergent. It means the series is not convergent. So the given series summation an is equal to summation 1 upon n की power p. So an is equal to 1 upon n की power p, which is greater than 0 for all n in n. So it is the given series is a positive term series. So what is Sn? Sn is a1 plus a2 plus so on an. That is 1 upon 1 की power p. So 1 की power p, 1 upon 2 की power p plus 1 upon n की power p. Okay. So here instead of taking m, we can take s2n. Here our m is m2n. We take m is equal to 2n. We can take any number. M is greater than n, right? So s2n is a1 plus a2 plus an plus 1 plus an plus 2 plus a2n. This is our s2n. So this is 1 upon 1 की power p plus 1 upon 2 की power p plus 1 upon n की power p plus 1 upon n plus 1 की power p plus 1 upon n plus 2 की power p plus 1 upon 2n की power p. So this is our S2n. So obviously 2n is greater than n. So for epsilon greater than 0, we can take epsilon to be however small. Even if we fix epsilon to be 1 by 2, epsilon equal to 1 upon 2, we fixed, right? It is greater than 0, we fixed. So we have to find S2n minus mod S2n minus Sn, which is less than epsilon. It means we have to show that this is less than 1 upon 2 if it is convergent. But if it is not convergent means it is not less than epsilon. If it is not less than epsilon, then what is the meaning of this? S2n minus Sn is greater than equal to epsilon. So we have to show that S2n minus Sn is greater than equal to epsilon, right? Because we have to show that this is divergent. If this is divergent, it means it is not convergent. If it is not convergent, so instead of proving this is less than epsilon, we have to prove that this is greater than equal. So what is S2n minus Sn? We have already write Sn and S2n. So we directly write first n terms are cancelled out. So we can write 1 upon n plus 1 की power p, 1 upon n plus 2 की power p plus 1 upon 2n की power. So because all the terms are positive, so we can skip the modulus. We can write 1 upon n plus 1 की power p, 1 upon n plus 2 की power p, and so on, 1 upon 2n की power. Because p is greater than p is less than equal to 1, right? So if p is less than equal to 1, so n plus 1 is n plus 1 की power p is less than equal to n plus 1. Is less than equal to, because p is less than equal to 1. If we take p equal to 1 upon 2, then under root of n plus 1 is less than equal to n plus 1. But if p is greater than equal to 1, then then the result is opposite. N plus 1 की power p is greater than equal to n plus 1, right? So if we take the reciprocal, 1 upon n plus 1 की power p and it is greater than 1 upon n plus 1. Greater than equal to n plus 1. So we again use the same inequality, right? So we can write this is greater than 1 upon, first term is greater than 1 upon n plus 1. So what is the result? What we can write for second term? It is greater than 1 upon n plus 2. Third term is greater than 1 upon n plus 3. And the nth term is greater than 1 upon 2n. Okay. Now we again find the relation between 1 upon n plus 1, 1 upon n plus 2, and 1 upon 2n. What is that relation? 2n, n is greater than equal to n, n is greater than equal to 1. If we add both side n plus n is greater than equal to n plus 1. Or we can say 2n is greater than equal to n plus 1. What is the reciprocal? 1 upon 2n is greater than equal to, less than equal to 1 upon n plus 1. Or we can say, or 1 upon n plus 1 is greater than equal to 1 upon 2. So similarly, what is the result for 1 upon n plus 2? It is also greater than equal to 1 upon 2. And up to so on, 1 upon 2n, that is equal to 1 upon 2. So we can write greater than equal to, because in greater than equal to, either it is greater or equal. Only one and only one condition is satisfied. So we can again write this as this is greater than equal to 1 upon 2n plus 1 upon 2n plus 1 upon 2n plus 1 upon 2n. Now think about this. I have already discussed, if we have to find a relation between A less than equal to B, we have to move like A is less than equal to lambda, lambda is less than equal to mu, mu is less than equal to some delta, delta is less than equal to B. So now you think S2n minus Sn, we have to find this is less than epsilon. If it is not less than epsilon, then it is not convergent. So we first write this term, this is our A, or we can say this is our A. We have to show that this is less than epsilon. It means we can find the relation. First, this is greater than this. This is our lambda. And then this lambda is to be related with mu. This is our mu. Now we can write this is equal to n upon 2n. Why we can say this is n upon 2n? Because this is up to nth. We have taken 2n terms. 2n minus n, then we have only n terms. So this is n terms. So n upon 2n, that is equal to 1 upon 2. So what is the conclusion now? That is mod S2n minus Sn is greater than 1 upon 2 for all n in natural number. You can take any natural number. This is what it is. Or, right? So it means mod of S2n minus Sn is greater than epsilon for all, even we can say greater than equal to n for all n belongs to natural. So sequence Sn is not convergent. Is not convergent. If the sequence is not convergent, sequence of partial sum is not convergent, then the series An is not convergent. And because it is a positive term series, so we can say summation An is divergent. And what is summation An? That is summation 1 upon n to the power p is divergent. But what is the value of p for p less than equal to 1? Pause, revise, and then proceed. let us do one more example. Use Cauchy criteria to show that the series 1 upon 2n minus 1 is divergent. Again, by Cauchy criteria, we have to show that this. So now, here the series summation an is equal to summation 1 upon 2n minus 1. So an is equal to 1 upon 2n minus 1, which is greater than 0 for every n. So we have a positive term series. So either series is convergent if it is bounded above, and this series is divergent if it is unbounded above, and it diverges to plus infinity. So as let epsilon d equal to 1 upon 4 greater than 0 be fixed. So we fix epsilon. If we not fix this, then again no problem. Okay. So we find S2n, the difference of first 2n, sum of first 2n terms of the series to the difference of first n term of the series, S2n minus Sn. What is S2n? So first, what we do, we find Sn and S2. So Sn is A1 plus A2 plus A3 plus An. That is 1 plus 1 by 3 plus 1 by 5 plus 1 upon 2n minus 1. This is Sn. What is S2n? A1 plus A2 plus An, and then An plus 1, An plus 2 plus A2. So 1 plus 1 by 3 plus 1 by n, even 1 upon, not 1 upon n, plus 2n minus 1 plus An plus 1 is 2n plus 1 plus 1 upon 2n plus 3 plus 1 upon 4n minus 1. So when we find the difference mod S2n minus Sn, we get first n terms are cancelled out. So we have 1 upon 2n plus 1, 1 upon 2n plus 3 plus 1 upon 4n minus 1. So this is equal to, we can skip the modulus. So we can write this as 2n plus 1, 1 upon 2n plus 3 plus 1 upon 4n minus 1. So now again we have to find the relation. We have to find the relation with this term. 4n is greater than 4n minus 1 for all n in natural number. You can take any natural number. 4n is greater than 4n minus 1. So what is 1 upon 4n? This is less than 1 upon 4n minus 1. So 1 upon 4n minus 1 is greater than 1 upon 4n. Similarly, 4n is greater than 2n plus 1. So 1 upon 2n plus 1 is greater than 1 upon 4n. So we try to find out relation like this. So this is greater than 1 upon 4n plus 1 upon 4n plus 1 upon 4n plus 1 upon 4n. And because we have only this, we have n number of terms, so we can write this as n upon 4n. And this is equal to 1 upon 4. What is epsilon? It is 1 upon 4. So it means mod S2n minus Sn is greater than 1 upon 4 for all n. You can take any natural number. So this implies that sequence Sn is not a Cauchy sequence. Hence, sequence Sn is not convergent. This implies series An is not convergent. Not convergent, that is, summation An is divergent. Because why we say it is divergent? Because An is greater than 0 for all n in n, and a series whose terms are positive, if it is not convergent, then it is divergent. So in this way, we can show that the series convergent or divergent by using Cauchy criteria. Now, prove that, show that the series summation 1 upon n factorial converges. So An is 1 upon n factorial, and we know that this is greater than 0 for every n in n. So what we do, if we know the result, so if An is greater than 0 for all n in n, and the partial sum Sn, if and there exists a real number k greater than 0, such that or we can say An is and Sn is equal to A1 plus A2 plus An, A1 plus A2 plus An, then summation An is convergent if and only if there exists k greater than 0, k be any real positive real number, so that Sn is less than k, Sn is bounded above. If this result holds, if Sn is bounded above and An is greater than 0, then we can say the series converges. So we use this result. So An is greater than 0, it is true. So first condition is satisfied. Now what is Sn? Sn is equal to A1 plus A2 plus An. We have to show that if Sn is bounded above, then it is convergent. Because it is if and only if case. Result is true for both ways. So A1 is 1 upon 1 factorial, A2 is 1 upon 2 factorial, and so on. An is 1 upon n factorial. Again, we follow the result. We can compare this with 1 plus factorial with 2 square, 1 upon 2 plus 1 upon 3 factorial. We can write this as 1 upon 2 square plus so on. 1 upon n factorial, we can write this as 2 to the power n minus 1. So we compare this with 2 to the power n minus 1 is greater than n factorial. So n factorial is greater than n factorial is greater than or equal to 2 to the power n minus 1. This. But 1 upon n factorial is less than equal to 1 upon 2 to the power n minus 1. So this is the inequality we use. Think again, A is less than B, so A is less than lambda, lambda is less than mu, mu is less than B. We have to reach up to B, but we use some lambda and mu relation between A and B. So यहाँ से इसके आगे what we do, we find the relation between factorial with 2 to the power n minus 1. Now because it is a GP series and it is a finite geometric progression series, so the sum is a plus 1 upon r raised to power n, so r is 1 upon 2, even a into 1 minus r की power n, a is 1 minus r की power n upon 1 minus r, 1 minus r, r is 1 by 2, and that is equal to 2 into 1 minus 1 upon 2 to the power n. So that is equal to 2 minus 1 upon 2 to the power n minus 1, and which is less than equal to 2, less than equal to 2 for all n. You can take any n, right? So this implies that sequence Sn is less than equal to 2 for every n in n. It means we find k is, that is 2. This implies sequence Sn is bond readable. Thus, we can say the series, the given series summation an is convergent. What is that series? That is summation 1 upon n factorial is convergent. So based on this topic, try to solve some more example. We will do comparison test and P test in the next video lecture. Thank you. Have a nice day.